Morning, students. Myself, Vijay Shankar from ECE Department, Chevrolet Engineering College. Today, we are going to discuss about the topic electric field intensity due to infinite sheet of charge in the same unit of electrostatics, third unit. We already discussed the electric field intensity due to infinite line charge and electric field intensity due to the charged circular ring. And another one is also there, that is electric field intensity due to the infinite sheet of charge. You see here, electric field intensity due to the infinite sheet of charge. See, in this diagram, there is a sheet of at x z is equal to 0 xy plane. On that, I assume here on that a small differential surface. Consider an infinite sheet of charge having uniform charge density rho s placed in xy plane as shown in the figure here, and consider as a cylindrical coordinate system. The point P at which let us see the point P at which E bar to be calculated on is on the z-axis. Consider the differential surface area. Consider the differential surface, a small differential surface area ds carrying a charge dq. Carrying a charge. Total the sheet is the charge is uniformly distributed, and we considered only the differential surface, a small differential surface area. In that, a charge is a change of a small differential charge dq. The normal direction to the ds in the z direction. You see, it is in the z direction. Whenever that is a sheet normal to the z direction, the sheet is at the x and the y. When we consider it as a cylindrical coordinate system, the x is r and the y is a phi and the z. Means the differential surface area normal to the z direction. Differential surface area normal to the z direction. The ds z bar is equal to. What are the differential elements here? The d for r direction, the dr, and phi direction r into d phi, and for the z direction it's a z dz, because we are considering as a cylindrical coordinate system. So ds z bar is equal to only we have the two, the remaining the two, the dr into r d phi a z bar, because it is in the z bar direction. Okay, my dear students. ds z bar is equal to dr into r d phi a z bar. Got it? So now here the normal direction to the ds z direction, hence the differential surface area normal to z direction is r dr d phi. R dr d phi in along the z direction. So a z bar. Only they are taking the magnitude here. The differential charge dq is equal to rho s into ds, because we are considering as a differential surface. So differential surface means the ratio between of the differential dq by the ds is equal to rho s. The dq is equal to rho s into ds, and that differential surface area normal to the r z direction, the rho s into r dr d phi, and it is a az bar actually, the az bar. Hence the de bar is equal to the de bar, the differential electric field intensity for the point charge is a dq by 4 pi epsilon naught r square into ar bar. Substitute the dq here, dq, as I'm taking only the differential charge only. It is not the vector form. Whenever if it is a vector form, definitely can use this a z bar. So dq is equal to rho s r dr d phi whole divided by 4 pi epsilon naught r square into ar. Got it, my students? Now, see in this figure, a small differential surface, and that there it is a charge is dq, and ar bar in the negative direction minus ar bar, because we take the point of P is on the z-axis, where we can find out the electric field intensity E bar. So this is a right angle triangle, and the distance you can find out AR bar is equal to the AR bar component is there and the Z bar component also. So what are the points we get? That is a Z into AZ bar and R into AR bar. That AR bar is in the opposite direction. So minus. So the R bar distance, we'll get as R bar is equal to the two components. One is Z into AZ bar minus R into AR bar. Because why I am taking the minus sign means it is in the opposite direction. R is in the positive direction towards downwards, and it is opposite direction is a minus AR bar. Got it, my dear students? Now the R bar is equal to Z into AZ bar minus R into AR bar. Okay. So the distance vector R bar has two components as shown in the figure. The two components is the radial component of R along minus AR bar is a minus AR bar, and another component along the Z direction is a Z into AZ bar. With these two components, R bar can be obtained from the differential area towards the point P as R bar is equal to minus R AR bar plus Z into AZ bar, and its magnitude is under root of AR bar coefficient is a minus R square, and the AZ bar coefficient is a Z under root of R square plus Z square. So to find the base vector, of R bar by the magnitude, R bar is a minus R AR bar plus Z into AZ bar under root of R square plus Z square. So substitute this AR bar, the base vector. This is a base vector. So base vector D bar is equal to, already we have the rho s R dr d phi 4 pi epsilon naught R square. R square is a magnitude under root of R square plus Z square whole square, and AR bar is minus R AR bar plus Z into AZ bar under root of R square plus Z square. Okay. For infinite sheet of XY plane, R varies from 0 to infinite, where phi varies from 0 to 2 pi, because the dr is there and the d phi. So d phi is only the phi direction, that varies from the 0 to 2 pi, and R is varies from the 0 to infinite. As there is a symmetric about the Z axis from all radial direction, all AR bar components of E bar is going to cancel, because there is a small differential surface area we are assuming in the R direction. So R is having the positive and the negative, both are the same. So are going to get cancelled. So eliminating of R component here, only we have the Z into AZ bar. We previously seen in the circular ring also, we eliminate the R bar component, and in the infinite line charge, we eliminate the Z. Why it is means the charge is on the Z axis, uniformly distributed. On that, we assume a differential charge dq, and here we are assuming the differential charge on the sheet. So the R component is eliminated, because the Z axis from all the radial directions, all AR bar components of E bar are going to cancel each other, and net E bar will not have any radial component. That radial component is AR bar. Okay. Now see, hence in the integral E d bar, there is no need to consider AR bar component. Hence, while in the integrating d bar, there is no need to consider the AR bar component, though it is considered after integration procedure will mathematically cancel. If you use that, or otherwise both will get the same answer only. It is whenever you are using the AR bar component and proceed the simplification in the integral, finally you'll get the 0 for AR bar component, not mathematically it is a cancel. So the DE bar, the rho s R dr d phi 4 not you see the under root will get cancelled here, R square plus Z square, and here the under root is there, R square plus Z square whole power 1 and whole power 1 by 2. Both the denominator is R square plus Z square whole power 3 by 2. And we take only the Z component, not the R component. Z into AZ bar, the numerator is the same. Apply the integral here, and the phi is 0 to 2 pi, and the R is 0 to infinity. So for the simplify or the apply the integral here, R square plus Z square is converted into mu square. R square plus Z square is converted into the mu square, and apply the derivative on both sides with respect to the R and the mu here. dr, R square is a 2R into dr, and the Z is a constant. The mu square is a variable we are taking. The 2u into mu. Got it, my students? For simplifying this integral value, I use that as R square plus Z square as a mu square. And apply the derivative on both sides with the constant of Z. Assume R square is a 2R dr and mu square du mu. So whenever I am changing these R values as of mu value, R into the Z, so change for R is equal to R, when R is equal to 0, what is a mu? dr, and the dr is changes as a du. So when R is equal to 0, these R values and these values are the phi values. When the R is equal to 0, what is the mu? When substitute the R is equal to 0 here, mu square is equal to Z square, nothing but mu is equal to Z. Then when R is equal to infinite, R is equal to infinite means infinite plus anything is infinite, and the mu is also infinite. So changing the R value in terms in the mu value, and the limitations is also changes. Mu is equal to Z to infinite. Mu is equal to Z to infinite when R 0 to infinite. So rho s R dr d phi is there. So you'll get R dr 2 to get cancelled, 2 to get cancelled. R dr, whatever the R dr is replaced with the mu into d. D phi is the same thing, and the rho s is also same thing, and Z into AZ bar is also same thing. 4 pi epsilon naught, the total R square Z square is a mu square whole power 3 pi. Got it, my dear students? So now the integration is only for the mu and the Z, not the Z, phi. Mu and the phi, sorry. Mu and the phi on. So mu integration is a Z to infinite, and the phi integration is for the 0 to 2 pi is a upper limit and the lower limit. Okay. Now you can see in this rho s by 4 pi epsilon naught and the Z, the total is a constant. Rho s by 4 pi epsilon naught, Z and AZ bar also. And we have only the integral of 1 by mu square into du. Another integral is there, that integral is a d phi. So mu is varies from the mu is equal to Z to infinite, and phi varies from 0 to 2 pi. The remaining all the terms here, the rho s pi 4 pi epsilon naught Z and AZ bar is already the constants. So what is a 1 by mu square into du? The mu square is a mu power minus 2. So mu power minus 2 plus 1 by minus 2 plus 1 in the denominator. So 1 by mu, the minus 1 by mu, with upper limit is infinite and lower limit is Z. Okay, and the phi, the integral is a integral d phi is a phi only. Upper limit is 2 pi and the lower limit is a 0. Got it, my dear students? So the rho s by 4 pi epsilon naught Z into AZ bar, and here the integral of phi is becomes of pi with upper limit is a 2 pi and lower limit is a 0, and 1 by mu square is a 1 by mu minus 1 by mu with upper limit is infinite and lower limit is a Z. So after taking the 2 pi here, the rho s by 4 pi epsilon naught Z AZ bar, and taking the upper, substituting the upper limit, we have only getting the 2 pi minus 0, it's a 2 pi only, and substitute the mu value is a infinite. So minus 1 by infinite is a minus 1 by infinite is a 0, and again there is a minus into minus, it becomes a plus. In the second lower limit, you can substitute 1 by z. 1 by z. So 1 by infinite is a 0. So finally, the 2 pi is get cancelled here. We'll have only the 2. And z is also get cancelled. And the remaining terms is rho s by the 2 epsilon naught and az bar. Az bar. And this 1 by infinite becomes a 0. So the E bar is equal to rho s by the 2 epsilon into az bar volts per meter. This equation will get for the electric field intensity due to the infinite sheet of charge. Electric field intensity due to the infinite sheet of charge. What it matters. It is also very important. One of the application in that. See, normally the Az bar in the direction normal to the differential surface area ds considered, hence in general it is a an bar. We consider it as a direction. If suppose it is another direction, means we can keep that it is a general value is a an bar, either it is a ax, az, ay, whatever it is. The direction normal to the surface. So thus for the points below the xy plane, an bar is equal to minus az bar, and it becomes of for points below the xy plane. See why they are saying that below the xy plane means, see, whenever if it is at z is equal to 0, the xy plane, the sheet is on the origin xy plane. When this is kept in, the sheet is at the origin. See, this is the xy plane. Whenever the sheet is in the below the origin, these are above the z-axis and these are below of the z-axis. Now the sheet is on the middle at the z is equal to 0 plane, 0 xy plane. When it is in the below, definitely this value is in the minus only. The direction is a minus. So that finally, they are concluding that that's for the points below the xy plane, an bar is becomes of minus az bar. The previously this az bar is a positive direction. It is the below the xy plane when considered as a point P. Let us take here the same thing. When I am taking it is a point P here, then it is the below the point P. It is a minus z bar direction, minus z bar direction. Okay, like this. When I am taking the negative direction, and this is a differential surface, the point P is here. Point P is here, means the R bar component. So this direction is a minus az bar. Minus az bar. Okay. The next another one important topic is a spherical shell of charge. Spherical shell of the charge. So suppose in this diagram, consider an imaginary spherical shell of a radius a. The charge is uniformly distributed over its surface. Remember, my dear students, the charge is uniformly distributed over its surface. That is a positive charge. Because whenever you can take the positive charge, the magnetic lines of force is terminated from the positive charge, and it is not terminated, not is generated from the positive charge, and it is terminated towards the negative, or otherwise there is any negative charge is there, it is terminated at the negative charge. Okay, this is a rho s. Let us find the E bar at a point P. Here the point P, located at a distance r. The radius of the circle, the spherical shell is a, and we are assuming a one Gaussian surface. On that Gaussian surface, radius is r, and on that we assume a point P to find the E bar at a distance r from the center, such that r is greater than a. R is greater than a, and r is less than are equal to A using the Gauss law. And we can, now I am considering it is R is greater than E. If suppose this Gaussian surface is on the circle and inside the circle is the another one. The first case, if I am taking the R is greater than E, the point P is outside the shell. The point P is in the outside the shell, the Gaussian surface. So consider the point P at a distance R from the origin, which is R is greater than A. The Gaussian surface is passing through the point P is a concentric sphere of radius R. See, the Gaussian surface of the flux lines is directed radially outwards and normal to the surface. See, whatever the magnetic lines will generate from the positive charge because the spherical shell is uniformly distributed outside, there is a positive charges, and all the radial lines is passes to this Gaussian surface. Wherever on that Gaussian surface is small differential surface we assume at point P to find out the D bar or the E bar. And the normal to the surface as the electric flux density D bar is also directed radially outwards at the point P and has a component along, not the long component only in the AR direction. Consider the differential surface area at point P to AR bar direction. Hence, the differential surface area normal to AR direction. This is a spherical shell means spherical coordinate system. In the spherical coordinate system, the dr, r into d theta, and r sine theta d phi is a differential elements or the differential components. And the differential surface area normal to AR bar direction means ds r bar. ds r bar is equal to r bar means there is no any differential element. R is only the direction, and the remaining components. These are remaining components r d theta and r sine theta d phi. R sine theta d phi. Got it, my dear friends? So now r into r it becomes of r square sine theta, r square sine theta, d theta, and the d phi is a differential surface area normal to the r direction. If it is a magnitude, only we can take the r square sine theta, d theta, and d phi. So we know that according to the Gauss law, q r psi is both q r psi is equal to integral d bar dot ds bar, d bar dot ds bar. The derivative can apply the d psi is equal to or dq is equal to d bar dot ds bar. Now I am taking the d bar as in the radial component of AR. So dr into AR bar dot r square sine theta d theta d phi AR bar. That is a ds bar. When I am taking that bar means it is a vector and there is regard to show that is a bar direction also. So AR bar dot AR bar is equal to 1 and the dr r square sine theta d theta d phi. Okay. Now, psi is equal to apply the integral, the surface integral dr r square sine theta d theta d phi. What might I say? In this integral, we have only the with respect to the theta and with respect to the phi. Dr and r square is the components of the constants. The phi is varies from 0 to 2 pi and theta is varies from the 0 to pi minus in the spherical coordinate system. So sine theta d theta d phi. So psi is equal to dr r square sine theta integral is a minus cos theta and theta varies from the 0 to pi and integral d phi is a phi, the 2 pi and the 0, upper limit and the lower limit. So in this substituting the 2 pi is upper limit 2 pi and the cos pi is a minus 1, minus into minus is a plus, cos 0 is equal to 1. Okay, that is also the minus, we'll get the 2 dr r square and the 2 pi and the 2 here See, once again, I will tell that is a minus cos theta by the pi and the 0 minus, you can write in the outside, cos pi minus cos 0. What is the cos pi value is minus 1, cos 0 is equal to 1, and minus 1 is a minus 2, and is multiplied with the minus is a 2 only. So for this, it's a 2 pi. The 2 into 2 pi is a 4 pi, 4 pi r square into dr. So psi is equal to q, we know. Psi is equal to q. When in a closed surface, there is a inside is a positive charge, and from the positive charge, there is a magnetic lines of force is generated, and it is a passes through the closed surface where we can assume a small differential surface there, and the leaving the outside magnetic lines is equal to the inside the charge, that is a q. So psi is equal to q according to the Gauss law. Q is equal to 4 pi r square into dr. What is the dr now? The dr is equal to q by 4 pi r square. dr is equal to q by 4 pi r square. Then d bar is, we assume the d bar is in the r bar direction, the dr into r bar. So q by 4 pi r square into r bar. And by using the relation between the d bar is equal to q by 4 pi r square into r bar. And now the relation between of the electric field intensity and electric flux density is a d bar is equal to epsilon naught into E bar. So E bar is equal to d bar by epsilon naught. D bar by epsilon naught. The d bar is a q by 4 pi epsilon naught r square into r. Got it, my dear students? E bar is equal. Understood? This is a point charge of electric field intensity and the point charge of the electric flux density formulas. Then this R is greater than A. For R is greater than A, the field E bar is inversely proportional to the square of the distance from the origin. So Q is equal to rho S into surface area of the shell. Surface area of the shell. If the surface charge density is a rho S, when we consider it is a rho R is greater than A, it's inversely proportional to the square of the distance. So Q is equal to rho S into surface area of that shell. What is that surface area of the shell is a 4 pi r square. That r we are taking as a A here. 4 pi a square. Shell radius is a. So 4 pi a square. So rho S into 4 pi a square. Q is equal to. You can substitute in the E bar is equal to Q by 4 pi epsilon naught r square into r bar. That Q is equal to rho S 4 pi a square. 4 pi get cancelled. This is a formula for the point charge of electric field intensity is a q by 4 pi epsilon naught r square into r bar by difference. That q, when we consider as a spherical shell with the radius of a, the surface area of the shell is a 4 pi r square. Actually, the r is here the a square with the radius of a. Okay, 4 pi get cancelled, and it becomes of rho S a square by the epsilon naught r square into r. And similarly, the d bar is equal to rho S a square by r square only because of relation between of d bar and e bar is a epsilon x. Epsilon does not get cancelled. Got it, my dear students? Now, in the second case, consider in the second case, consider the Gaussian surface is inside the circle, outside the circle of the spherical shell. Now it is on the circle, on the spherical shell. R is equal to A. R is equal to A. Okay, R is equal to A means we already got that E bar is equal to Q by 4 pi epsilon naught R squared is. Now R is becomes of A square into R bar volts per meter, the electric field intensity. Now, consider the point, the Gaussian surface inside the shell. Now it is outside the shell one time R is greater than, and on the shell R is equal to. Now inside the shell, whenever considered the R is there, the Gaussian surface, but there is no any effect on the Gaussian surface because the charge is uniformly distributed outside. Get in the outside only. So if it is in the outside, Gaussian surface is outside, there is an effect is there. On the circuit, on the shell is also there is an effect is there. But whenever if it is inside, there is no any effect on the Gaussian surface. So it becomes a 0. It becomes a 0. The magnetic lines, the Q is equal to 0. See the Gaussian surface passing to the point P is again the spherical surface. The radius is R is less than. But it can be seen that the entire charge is on the surface. No charge is enclosed by the spherical shell. And when the Gaussian surface is such that no charge is enclosed, irrespective of any charge present outside, the equal to 0. The d bar dot ds bar is equal to 0. Got it, my dear students? The R is less than, the term is a 0. And finally, the answer to satisfy the total charge enclosed is a 0 inside the spherical shell. D bar is a 0 and E bar is also the 0. See here, for the three cases, R is less than A, the E bar is equal to 0. R is less than A, where R the value is there in the x-axis and E bar you can take in the y-axis. For the first case, R is greater than, we'll get the Q by 4 pi epsilon naught R square into A R bar. E bar is equal. And R is equal to A, Q by 4 pi epsilon naught A square into A R bar. And R is less than A is equal to 0. So R is less than A, the value is 0. And when R is equal to A, becomes of Q by 4 pi epsilon naught. And R is increases, definitely the curve is decreases like this. Means one now the denominator is increases, and the denominator is increases, definitely the E bar, the numerator is decreases slowly. So you'll get the characteristics like this. When R is less than, the value is a 0, and R is equal to A is a Q by 4 pi epsilon naught R square, and R is greater than A, it goes on decreases. After R is equal to A, the E bar is inversely proportional to the square of radial distance. Inversely proportional to the square of radial distance of a point from the origin. Got it, my dear? So we'll get the characteristics like this of the three cases we assume. So variation of D bar again or not into epsilon. Got it. Now the same thing we can take as a spherical shell uniformly charged distribution inside also. Outside and inside. Totally it is a volume. Previous case we assume the surface only the charge is on the surface. So when we consider outside, there is a effect is there which is passes through the surface. On the shell also the side. Outside on and the inside also there is an effect because inside there is a charge is there. Now because it is considered as a volume, the rho v. If it is greater than A, also effect occurs, and inside also on also is affected by 4 pi r square. The same thing is there, and it is R is equal to A, there is effect, and R is less than A is also you get the D bar. There is a Q by 4 pi R square and Q by 4 pi epsilon naught for the E bar. So variation is there. It is not the 0 from less than. It is slowly it is increases and it is a decreases. Slowly increases and the decreases. Now you can see the first case Consider a sphere of radius A with a uniform charge distribution of rho v. The total charge is uniformly distributed so fully of that spherical sphere. And let us find the E bar at the point P located at the radial distance of R, that is a Gaussian surface at the point P. When R is greater than A, the differential surface area normal to R direction is the spherical coordinate system R squared sine theta d theta d phi. And using the Gauss law, d psi is equal to d bar dot ds bar. D bar we can consider as in the dr in the R bar component, R squared sine theta d theta d phi. R bar is equal to 1. And we have only the magnitude dr R squared sine theta d phi. And substitute that in the Gauss law, Q is equal to integral d bar dot ds bar. After simplifying, here the cos theta is a 2, and here the 2 pi, totally the 4 pi r square. And since the dr component, dr is equal to q by 4 pi r square, q is equal to, we got it. Q is equal to dr r square 4 pi. Now, what is the dr component here? Okay, q by 4 pi r square into r bar, and the relation between of electric field intensity and electric flux density d bar dot epsilon, q by 4 pi epsilon naught r square into r bar. These two formulas are for the point charge of electric field and electric flux. Okay, now the total charge enclosed can be obtained as q is equal to rho vd. This is a formula we know, my dear students, dq by dv is equal to rho v. So dq is equal to rho v into dv, and q is equal to rho v dv. So q is equal to integral rho v dv, and this integral having the volume is there. That volume means spherical coordinate system varies for the pi is 0 to 2 pi, and theta is varies from the 0 to pi. And now here the r is varies from the 0 to a, because the shell, spherical shell or the spherical sphere of sphere, it is a 0 to a, the radius one. So rho v into dv. What is the dv here? The r square sine theta dr d phi and the d theta. Got it, my dear students? The total that dv is equal to, dv means a differential volume. All the components is multiplied, r d theta and r sine theta d phi. These are the three differential elements in the spherical coordinate system. Combining of all these things is a dv. So dv I substitute r square, r into r square, sine theta, d phi, and dr. Okay, and that is equal to rho v, and integral of r square is r cube by 3 with the limits of 0 to a, and sine theta integral is a minus cos theta with the integrals of pi and the 0, and phi integral d phi is a phi with the limits of 2 pi and the 0. For these two, we'll get the 4 pi. Okay, 4 pi by 3 is a denominator as a rho v, and here the a we can substitute as r a cube, 4 pi 3 pi a. You see here again the rho v, and I'm substituting the upper limit is a cube by 3, and 0 the value is a 0, and these two combination is a 4 pi. So it becomes a 4 pi 3 pi a cube into rho v, because it is a q coulombs. Q is equal to this function is a coulombs. C is the unit of the charge. Got it, my dear students? So now we can substitute this q in the E bar. E bar is a 4 by 3 pi a cube rho v. It's whatever you got the q, and 4 pi epsilon naught r square. So 4 get cancelled, and the pi is also get cancelled, and finally we have the numerator a cube rho v by the 3 epsilon naught r square into r. So the relation between of d bar and e bar, we know there is no any epsilon in the d bar, a cube rho v by 3r square a. This is for r is greater than a outside the sphere, charged spheres. Okay. Now, if r is equal to a, r is equal to a, e bar is equal to, now r is equal to a means a cube rho v by 3 epsilon naught a square is there. Now that a is r is a square, so a cube and a square will get cancelled. You have only the a in the numerator. Rho v a by 3 epsilon naught a r bar. And the case is second case. Okay, d bar is equal to rho v a 3 only. There is no epsilon here because the relation between of d bar and a bar. Now the Gaussian surface is assumed inside out. In the previous case, surface, only the charge is on the surface, there is no any effect in the inside. Now it is a volume, there is a charge is inside also, there is an effect occurs. So we'll get the d bar. D bar in the r bar component, and d psi is equal to q is equal to d bar dot ds bar, and ds bar is along the r direction, so r bar r square sine theta d theta d phi, and d bar is equal to q by 4 pi r square, and d bar is equal to dr is equal to q by 4 pi r square, and d bar is equal to q by 4 pi r square into r bar. Got it, my students? Now the q is again, the charge is outside the Gaussian surface will not be affected the d bar, and the inside the q is equal to 4 pi 3 pi r cube rho v, the same thing less than, and d bar is 4 by 3 r cube rho v by 4 pi r square. The d bar is equal to r by 3 rho v, r by 3, because it is a r is there inside. So we got this q is equal to, in this function, the q is equal to 4 by 3 pi r cube rho v. In the first case, q is equal to, we got the 4 by 3 pi a cube. Here it is a 4 by 3 pi r square, because the Gaussian surface is inside the sphere, charged sphere, so r cube. So r and r get cancelled square. So d bar is equal to r by 3 rho v. Previous case, here d bar is equal to a cube by r square, because it get cancelled a cube by r square. And here only we get 4 by 3 pi r cube. The r square is get cancelled. We have the remaining r, and 4 is also e bar is equal to d bar by the epsilon naught. So the e bar is we get as r by 3 epsilon naught rho v to a r bar. Is the e bar in the third case. Less than the 0, it is a slowly increases. Why it is means you can see that if r is greater than, the graph of e bar is against r is a parabolic, while r is less than, it is a straight line. R is less than, it is a straight line. Why it is a straight line means, by the students, because r is there in the numerator. R is there in the numerator. See here, this is the equation. R rho v 3 epsilon naught. When r is increases 0, 1, 2, 3 means correspondingly it is a r is equal to a, it becomes of rho v into a 3 epsilon naught. Then whenever it is a decay, next is r is greater than e. Greater than a. So what is the equation we got for greater than a cube rho v by 3 epsilon naught r square. These are the three equations we got after deriving that r is equal to a, and r is less than a, and r is greater than. R is less than a is the equation. R is less than a, and r is equal to a. This is the equation. Is when r is less than a, the r is in the numerator, So when we are increasing this function 0 to up to the a, it is a linear function. At r is equal to a, the rho v into a, the 3 epsilon. And now coming to the greater than a, where the r is in the denominator. So when r is increases, definitely that curve is decreases. These are characteristics got after the Gaussian surface is zooming in the outside, inside, and on the sphere. Okay.